Hey guys, this video on acids and bases goes over the key definitions and the characteristics of strong and weak acids, and at the end some exam questions that will be useful for some A-level students. To kick things off, we have the Bronsted-Lowry theory, which aims to define what acids and bases are. In this case, an acid is a proton donor, whereas a base is a proton acceptor, and the proton is simply drawn as a H+ ion. These are the terms to learn for easy marks. If we get a real example of hydrochloric acid reacting with ammonia, you can see that the HCl donated its H+ ion over to the NH3, which has accepted it to form an ammonium ion. So the HCl is the acid, whilst the ammonia is the base. This is the main term you use, as H+ is used to characterize the strength of acids. However, there is a major limitation to this theory. Not all reactions include a transfer of H+ ions. Which introduces us to the Lewis theory. It's a more general definition as it explains the reaction in terms of electron pair exchanges, which all reactions undergo. In this case, the acid is an electron pair acceptor, whereas the base is the electron pair donator. This theory can explain to us why acids like boron trifluoride are actually acids, despite having no hydrogen atoms to donate. Take the reaction with ammonia. You see the boron has 3 valence electrons which it shares with 3 fluorines that provide an electron each. Boron therefore has 6 out of the 8 electrons needed to fulfill the octet rule, so it has an empty p orbital, which is shown by the white dumbbell shape. The nitrogen, however, has 5 valence electrons, 3 of which is shared between the 3 hydrogens, so it does have its 8 electrons. 2 of these electrons are a lone pair. Now it's this lone pair that gets donated to the boron's empty orbital to form a covalent bond. This is an acid-base complex, and typically occurs in compounds that have empty orbitals or lone pairs. Following that are conjugates. Every acid has a conjugate base, and every base has a conjugate acid. And what I mean by this, let's say we're given the reaction of ethanoic acid. You can see is in equilibrium. That means if the reverse reaction were to occur, the ethanoic anion on the product side now acts as a base, whereas the hydroxium ion is an acid. These are known as conjugate pairs. What's useful to know is that the H3O+ is just another way of writing H+ for a proton. We do this because protons don't like to live on their own and is typically bonded to water. Next we get to go on to acid strengths, and strong is most definitely the easiest to understand and use. A strong acid fully dissociates in solution. This means a compound that breaks down to donate all of its protons is a strong acid. Knowing this, it is then quite easy to quantify the strength. So let's look at a basic reaction. We have the acid A with its hydrogen reacting with a water base to form its conjugate, and again it is in equilibrium. To know its strength, we want to know where in equilibrium it is. And by using the equilibrium constant Kc, it tells us how complete a reaction is at equilibrium. Kc is defined as the multiplication of the concentration of the products over the reactants. However, when we deal with acids, we make an assumption. We say that the concentration of H2O is essentially constant throughout, as it is in such excess. Concentration is far too high, so we just ignore it. We can change our constant around to be Ka, the acidity constant. So for a strong acid, we know that the acid fully breaks down into its ions. So the value for product will be large and the reactant will be small. This will create a very large Ka value, and that's the thing to remember. For a strong acid, Ka is a very large number, even to the multiples of 10, like HCl. Up next are weak acids. Weak acids do not fully dissociate in solution. So in terms of equilibrium, it could rest anywhere, but typically favours the reactants. And if that's the case, if we put it in our Ka equation, the product will be small and the reactants will be large. Meaning for a weak acid, it is important to remember that Ka is a very small number, to many decimal places. But all of these giant numbers are tedious to record, so we have pKa values to make them more digestible, defined by the minus log of Ka. So let's bring out the whiteboard. We can calculate the pKa of hydrochloric acid with its Ka value. A strong acid, and we can see the pKa is -7, a very low number. Whereas the weak ethanoic acid has a pKa of 4.76, which is a slightly higher number. So for pKa, low values are strong and higher values are weak. Definitely make sure you can wrap your head around these two terms. That way you can quickly determine the strength of any given acid in the exam. This leads to pH, where the bulk of exam questions will be, and is the final topic of this video. pH is a measure of concentration of hydrogen ions in solution. If you're asked to define pH, always write down the equation. On the pH scale, 1 is the most acidic, 7 is neutral, and 14 is alkaline. Let's look at an example question. You're given HCl with a concentration of 0.15 moles per decimeter cubed. What is the pH? First step we should take is try and determine the strength of the acid. HCl is a strong acid, so we know it fully breaks down into its ions in a 1:1 ratio. So the concentration of the acid is going to be the same as the H+, so you can simply just put it into the pH equation to get the value of pH. Weak acids, on the other hand, take a lot more work. It means they're worth more marks, but think of it as a good thing. Given the same concentration of ethanoic acid, what is the pH? See, we're also given the Ka value, which is quite small, so we know that the acid is weak. So what do we know about weak acids? Well, they don't fully dissociate, so we will need to work out what the concentration of H+ will be, and we'll use the Ka equation. Yet again, there is an assumption we make. Since the acid breaks down to its ions on a 1:1 basis, the value of the conjugate base and the conjugate acid will be the same. That way we reduce the number of unknown terms, and we're just going to denote the concentration of H+ as the letter X for the sake of this example. We get our new equation with x squared, and underneath it is the acid minus the amount of acid that was used to form X. Subbing in our numbers and rearranging gets a quadratic equation, which we can use the lovely quadratic formula to get X. Really care about the positive number, as you can't have a negative concentration. Since X is the concentration of H+, we can just sub it into the pH equation to get 2.80. And pH is unitless, we don't have to worry about units. However, this is all rather long-winded, and you can see that our value of H+ is tiny compared to the starting acid, so I think we can afford to make another assumption, just to make the calculation quicker and easier, to not waste time or increase error in the exam. We just assume that the starting acid concentration doesn't change at all. We can simply multiply the Ka and the acid concentration, square root to get our H+, and sub in the pH just to get the same value, the 3 decimal places. That's definitely the method you should use in the exam. And that concludes this video. Thanks for watching, and good luck in your studies.